Right, I hope the audio is better on my phone. Effectively, right, the whole idea came from looking at the way we use names to represent lineages. The only permanent, like, fixed element of the name is, like, your father's last name. Like, that will carry throughout all the sons. Whenever there's, like, a family that has, like, no sons, their last name fully dies. Whenever a woman marries into the family, their lineage is also not represented at all. This is not, like, a real problem. We have, like, modern systems to just track who gave birth to who. But I assumed that there was, like, a correct mathematical solution to this problem, like a way to, like, represent both the mother and the father's name in, like, a finite length name and have that propagate through generations as more names get added. I assumed this was a solved problem, but it's actually provably unsolvable because of some, like, really old theory on, like, information compression. You simply cannot represent, like, infinite amounts of information in any finite, like, data set, and so you have to take compromises. And so the question really is, like, is there a good standard set of compromises to take in order to solve this problem? And the answer is almost certainly no. There's not a good set of, like, standardized compromises to represent as much information as possible. Because, for example, we could do something like making names infinitely long, where, like, if my name was John Smith and I married Mary Jane, then all of our kids' names would be Smith Jane, right? And you would just keep doing that forever. And you have incredibly obscenely long names. I'm trying to solve this problem, essentially. I'm trying to solve this non-problem. It's really not a problem. I think it's an interesting thing to try to solve. I'm trying to solve this problem. I kind of decided I was going to limit myself to 30 syllables. Like, you can have a name that had 30 syllables. But maybe I'll limit it further now that the syllables are so, like, disgusting. But yeah, that's the idea, right? How can we represent names and have them propagate downwards through a lineage? It seemed pretty much like the best solution to this is something called a Bloom filter. You can do a little bit of binary arithmetic, but it's not too bad. Like, essentially, we can, like, combine bit strings. Like, if two people have, like, a bit string, and we just combine them so all the ones get, like, squashed down with, like, an OR function, and then that becomes, like, the name of their kid. Like, that bit string will then represent their child. Think of it like this. There's two people, right? One of them is named 01, and one of them is named 10, and their kid is named 11. So this one had, like, a 1 in the first spot, this one had a 1 in the second spot, and their kid's name has a 1 in both spots. That's how this works, except the idea is you want the bit string to be as big as possible because it gives you the most representable values. Okay, so issue 1 with this, which I won't get into too much, every generation, the names become 50% similar, right? And in an infinite amount of generations, everybody's name will be 1 because everybody will be related to everybody, which means they would have the same name because it's lineage based, and I can't store infinite information. This is bad, and I'm doing a lot of things to fix that. There's a lot of, like, special techniques for fixing that, which are too complex. But what I want to talk about is the linguistics aspect of this, which is that when we have string like you know, ones and zeros all the way through, right? That is not, like, an actual name that you can say. So I'm trying to figure out how to represent those bits as like English-ish sounding phonemes. And this is, like, an easy problem, really easy, stupid easy. You can just take, like, random consonant, random vowel, random consonant. That's a syllable, and you can just do that. But it's actually a really interesting problem of, like, how can I do this maximally? How can I, like, juice squeeze the heck out of English by using every single consonant sound and every single vowel sound? And there are a lot. I'm going through the consonants and trying to get, like, as much as possible because the more there are. But there's a whole bunch of decisions I have to make of, like, what do I include as, like, a pronounceable phoneme? Like, what do I count as, like, a valid syllable? Is złość a valid syllable? I don't know. I think I'm gonna count it just for size, but it really is kind of a complex dilemma. And, like, another thing, you want locality, right? If you're related to somebody from 3 generations ago, your part of your name should sound like part of their name. Like, that's the whole point. Your name should sound similar if they're related, the same way, like, your last name sounds like your dad's last name, you know? But there's a real struggle in locality, in that if one bit changes, and it changes inside of a syllable that can represent a possible, like, 600 values, then how do I make sure the bit changes and sounds like the same syllable? And this is why I was talking about, like, n-dimensional hypercubes earlier, because there's a lot of math about this, about, like, essentially, with error correction, this is a very important thing, right? So a lot of people study this. There's things called gray codes. So, like, say this is 9 bits long. I can use a 9-dimensional hypercube. All the adjacent points to a given node on this cube should sound the same. When I want to build the encoding from binary to string, I then need to traverse this 9-dimensional hypercube and place all the actual phonemes on this cube. And that's how I keep things local. That's the strategy, at least.